Hello, everybody. Welcome to today's current seminar. Today we have one speaker. Our speaker is Tailin Wu. He will be giving a talk on wavelet diffusion neural operators for PD simulation and control. Tailin Wu is an assistant professor of AI at the School of Engineering at Westlake University, China. PI of AI for Scientific Simulation and Discovery Lab. He earned his bachelor's degree from Peking University and his PhD in physics from MIT. From 2020 to April 2023, he conducted postdoctoral research in computer science department at Stanford University. Tailin's research focuses on developing AI methods for scientific simulation, control, and discovery. His work, which is used for large-scale simulations of fluids, plasmas, energy, and other fields in physics, has been published at top machine learning conferences and top physics journals, and has been featured in MIT Technology Review. With that short introduction, the floor is yours, and you can start your presentation.
Okay, thank you very much for the introduction. Today, my talk is about wavelet diffusion neural operators for PDE simulation and control. So we all know that like PDE simulation and control are universal across different scientific and engineering disciplines. For simulation, like we can have like weather forecasting or combustion or plasma simulation and many other like fluid simulations. And for control, we also have many tasks like underwater robots and so on. So here, I would like to first set up the task. So suppose that we have a system whose state at time step t as ut. And then the task of learning the surrogate model for the PDE is as follows. Basically, we have the ut and we also have some external like control, which we call wt. And then we also have some static parameters, which we call gamma. And our goal is to learn a surrogate model f of theta, which can simulate the system forward in time. And then typically we learn it using like the mean square error loss that try to predict the next time step ut plus 1. And then we learn it by minimizing the mean square error. And then after we have learned the f theta, then we can perform autoregressive prediction. So that, for example, given the first state, initial state, we can then predict the next time step given the external control, and then we do it forward in time. And then in this kind of like simulation forward in time can be also think of as the like this decomposing this very complex probability distribution as the product of many conditional distribution. And since we are thinking about distribution, recently there are two very famous generative models. One is the large language models, and the other is diffusion model. And then the diffusion model is very good, highly complex distributions. For example, here we have the Sora, which can learn the conditional distribution of video given the text. And then we have the Stanford Aloha robot, which can learn the action, the probability of the action given the state. The advantage of the diffusion model is that it typically can learn a very complex high-dimensional distribution. Here, I will give a very brief review of the diffusion model. Basically, we have some data distribution, and then we have some data that are sampled from this distribution. And then in the forward process, we can have the adding the noise so that we can gradually add the noise to the data, and then gradually it will become a Gaussian distribution. And then at the same time, we can learn a denoising network that can gradually, step by step, denoise the Gaussian distribution back to the data distribution. If we can think of it as the data are living on a low-dimensional manifold on a high-dimensional space, then any data is a point in this space. And then the diffusion model is learning how can we denoise from a Gaussian distribution back to this data manifold. So the training of the diffusion model is very easy. Basically, we can sample a data point from the data, and then we can add t steps of Gaussian noise to the data. And then we learn a denoising network, epsilon theta, that predict the noise that is added. And then in the sampling process, we first start with sampling a sample in the Gaussian distribution. And then in each time step, we use the current like noise data and then use the learned model to predict the noise and then subtract the noise from our current data. And then after t steps of denoising, we can arrive at x0, which will look like a sample from the distribution. And we can also think of the diffusion model as learning an implicit energy-based model, where suppose that we are trying to learn data distribution, which is equal P theta of x. Then the energy can be think of as the negative log of the probability distribution. And then the denoising network can be think of as the gradient of the energy. And then the denoising process can be think of as we are starting at a Gaussian distribution, and then we follow the gradient of the energy, and then gradually we arrive at a low energy point, which is also a high probability point. And then if we want to like add some objective or constraint to this sample, then we can add the denoising process at objective J. And then basically what we do is that we change the previous denoising network by adding a gradient of the energy of the objective. And then we can also guide the sampling process to the point where the objective is low. This is called classifier-based line guidance. And then typically we can add some objective to this J, or we can add like physics-informed loss to this J. So then we can combine the physics-informed prior, and then we can also add some data prior, which is learned through the energy-based model. Therefore, if we want to use the diffusion model to model this simulation process, instead of doing the autoregressive generation from left to right, here we can do the denoising from up to down. Basically, we can regard the trajectory of the state from time step 0 to time step t as a joint variable together with the control sequence. And then starting from the Gaussian distribution, for all these variables, we can then perform multiple steps of denoising so that it can gradually generate the joint trajectory of the state together with the control sequence. And in the recent years, diffusion model has been applied to the PDE simulation and control. Its advantage is that it is very good at modeling the high-dimensional and long-term dynamics of the PDE systems. But also we find that it has two major challenges. One is that typically the diffusion model will first generate some low-dimensional, low-frequency like signal first, and then high-frequency signal last. And then there are typically some high-frequency information loss during the generation. Specifically, for example, here, suppose that we want to generate the PDE profile here, where there are some spatially abrupt changes. Then the diffusion model may be hard to generate these high-frequency components. Second is that typically in the diffusion model, we use a fixed size grid, which cannot generalize to finite resolutions. Here we want to exploit the advantage of the neural operator, which has the advantage that it can have the super resolution. So to address these two challenges, in this work, Wavelet Diffusion neural operator, we provide two aspects of solution to address the challenge. One is that instead of generation in the original domain, here we generate the whole trajectory in the wavelet domain, where we use the wavelet transform on both the space and time. And then the advantage is that the wavelet transform is both spatially and frequency localized. And it is very good at modeling the abrupt changes, those high frequency information. And then the other main contribution is that we can also use this wavelet transform and train it to generalize to higher resolution. Therefore, in the inference time, we can use our model to generate to even higher resolution than in the training. So here is the overall architecture of our model. I will introduce this one by one. So firstly, I will give some basis about the wavelet transform. So basically, we use the wavelet basis to represent some spatial and temporal trajectory. And then for the wavelet transform, we have two kinds of basis functions. One is the scaling function, which represent the general outline of the signal. And then we also have the mother wavelet phi, which can depict the detailed information, which are typically higher frequency. And then here are some often used like mother wavelet. And then for the wavelet transform, we typically have multiple levels of the basis. For example, here, we can scale the original wavelet basis using this 2 to the L. Therefore, the L here represents the level of the wavelet basis. And the larger the L, the more spatially localized it is for the basis, and the higher frequency it is. And then for the M, it is modeling the spatial location of the basis. And then therefore, for some signal or for some function, it can be represented as this wavelet transform, where we can use the coefficients of this basis to represent the whole signal. Note that here, for the first term, this term is used to represent the coarse wavelet coefficients. And for the mother wavelet basis, we have the detailed coefficient. Okay, so then once we have this wavelet transform, then we can perform the generation of the diffusion in the wavelet domain. Basically, previously we performed the denoising in the original domain, both in space and time. But here, for the trajectory of the system, for example, suppose that we have the 2D PDE, then we have 2 dimensions in the space and then 1 dimension in the time. Then we can perform the wavelet transform both in the space and time, and then use the coefficient as here in the CL and DL to represent both in space and time to represent this trajectory. For example, here the W U from 0 to T is a temporally extended trajectory that is 3 dimension, 2 for space and 1 for time. And then this W represents all the coefficient of the CL and DL. And here it is the inference procedure where just like in the previous diffusion model, here we are generating in the wavelet domain. We are starting from a Gaussian distribution. Here we are learning a diffusion model, a denoising network that can generate the wavelet coefficient in the wavelet domain. So the upper equation is for the simulation where we only want to generate the trajectory. But for the control, as I have shown before, we need to generate both the state trajectory and also the control sequence. Therefore, here we are generating both the F here, which are the trajectory, and the A here is for the control. Okay. Now we also address the challenge of the multi-resolution. Here is some basics. So suppose that we have a special domain like this, and then we also can maybe have a low resolution data where the spatially it is like half of the resolution. And then what we can do is that we can rescale this low resolution data to the same size as the high resolution data so that it can be more easily treated together. So what we do here is that in the training time, we learn a model that given the coefficient for the lower resolution data, the model is learned to generate the data, the coefficient for the higher resolution. Therefore, in the inference time, it can generate to even higher resolution than in the training. For example, in the training time, we give the model pairs of low resolution and high resolution. For example, 16 by 16 together with 32 by 32, and then 32 by 32 together with the 64 by 64, up to the dimension of 128 by 128. This is the highest resolution during training. But in the inference time, once the model have been learned, it has learned to generate from low resolution to high resolution. Therefore, it can generate to even higher resolution. For example, in the inference time, the condition may be the coefficient at 128 by 128. Then it can generate the coefficient at 256 by 256 up to 512 by 512. Therefore, basically, the model is learned to generate to even higher resolution than in the training. So here I will present the results. We test our model on 5 different PDE data. 3 data are 1D PDEs, and 1 is for 2D PDE, and 1 is the ERA5, which is a weather forecasting dataset. So here is the PDE simulation result. We compare our model with several state-of-the-art models like FNO and WNO, where the WNO is also using the wavelet transform. And we present the mean square error between the prediction and the ground truth. We can see that across different datasets, our model can achieve typically the best or the second best performance. Especially in the very hard ERA5, it also achieves the best performance.
Tailin, this is Lulu from Yale. So I have a question about the table here. So in this table
yes.
for the training, is the training data is clean data or the training data has noise?
The data all are presented the same. They are all clean data.
Oh, okay.
Yeah. For example, like we give them the data from the simulator, and then they are all clean data. Yeah.
Yeah. Then my question is, so for diffusion model, because each prediction is random, right? So how do you get
Yes.
the prediction?
Yes.
Do you do the ensemble mean or?
So here, for example, yeah, you are right that the diffusion model is like probability model. So each time they sample, they will arrive at some like slightly different result, right? But what we do to do the evaluation is that, for example, we given the initial state, we will generate the future trajectory. And then for each trajectory, we compare with the ground truth and compute the mean square error. We do not do the ensemble mean. We just regard each of the sample as the prediction.
Oh, okay, okay. You just use one random sample as
Yes.
the prediction.
Yes.
Oh, okay, okay, yeah.
And also we find that if for this system, actually they are deterministic. Therefore, we find that the diffusion model can learn to generate typically very the data with very low variance. Because the data that is learned has a very low variance. It's very deterministic. Mm-hmm. Yeah. Okay. Also, here we inspect whether our model can capture those very highly abrupt changes in both in space and time. So here it is a CFD data, the like Navier-Stokes in 1D, and the ground truth, which is the dashed line, is this. We can see that it has abrupt changes in space. And the DDPN is the diffusion model that are only doing it in the original space. And the purple line is our WDNO, which we can see that it can better match the ground truth. Also, here is evolution of the data of the profile across time. And then starting with here, we can see that around the time like 50, which is around here, it begins to have some abrupt changes in space. And then around the time in here, we see that the DDPN, which is the diffusion model in the original space, will have a much higher error that is increasing. But our WDNO model, which is this across, the error does not change much. Therefore, we can see that when there are abrupt changes occurs in time, our model can also do better than in the original space. Also, we do an experiment to test whether our model can generalize to higher resolution. So in the 1D Burgers equation, we can do the upsampling both in space and time. So here, one step of upsampling is like we are in the inference time, we perform our prediction both at 2 times the original spatial resolution and then 2 times in the temporal resolution. And then 3 times of upsampling will expand the space resolution by 8 and then the temporal by 8. And then we see that our model, which is the purple line, achieves the best log MSE compared to other model when we are doing the upsampling. And here is the 2D incompressible fluid after the upsampling in space. One step of upsampling is like 4 times of the size, because in the 2D, in the space, we upsampling by 1 time, it's like 2 by 2. And we can see our model can also do better than the other model. And also we compare our model with the temporal like evolution. So both the DDPN and WDNO, we generate all the future trajectory as a whole. Like we do not do the autoregressive like generation. Basically, we regard the full trajectory starting from Gaussian and then denoising to the data. Therefore, we can see that both our model and the DDPN the error versus time, the growth is slower. For other models that are doing the like autoregressive, they may have this error accumulation. Okay, then we also do the experiment of PDE control. Firstly, we are doing the Burger's equation control, where at each space and time, we can add some external control, which is the MT of NX. And then this can inject some source into the equation and then change the profile. Our goal is that after the control, we want our final state, final U profile to be as close to the target profile as possible. For example, like here. And at the same time, we may also want it to have a lower control energy. So the left table is the result, where we see that our model can achieve the best like mean square error between the final state and the target state. And we can compare with several important baseline. For example, the BC here is the behavior cloning, where the model just learns to predict the action given the state from the data. And then the BPPO here is the offline PPO network, offline PPO method, which is also a strong method typically. Then we see that our model achieves the best performance, which is slightly better than the DDPM. And then we also do the 2D control. Here, we are controlling smoke in the fluid, where we can see that there are fluid in this maze. And then we want to control this initial smoke through the maze to the upper exit. We want as many of the smoke to flat the exit as possible, but not going to other outlet. And the place we can control is only the outer part of the maze. We cannot control the inner part. Therefore, it is a indirect control. Also, there are around like 1,000 pixels in the outer part. So this is also a very high dimensional control. We see that our model can generate the control sequence that guide the smoke from the maze out to the exit. And here the number is the number of smoke that is not coming out from this red exit. And we achieve the lowest like leftover. Okay, so this work is done, is led by my student Peiyan Hu and also Ray Wang. And if you are interested, you can read the paper and also use the code. So since we still have some time, I will also introduce one of our recent work that following this work. So just now I have introduced that we can use the wavelet transform in the basically generation in the wavelet domain to perform the simulation and control. Apart from these two tasks, we also have two other tasks that are also universal in the science and engineering. One is parameter identification, where given the observation in some sparse observation in some time and space, we want to recover the full parameter of the system. And then we may also have the task of inverse design, where we want to design the parameter of the system such that the design objective is optimized. For example, we want to design the shape of the airplane such that the lift to jack ratio is maximized. So these four tasks are universal across science and engineering. But up to now, these four tasks are performed independently. So we develop different methods specifically for each task, where the model developed for each task may not generalize to across different tasks. So here, continuing from the previous works, where we can basically regard these 4 tasks all as generation. For example, the simulation, we can think of it as generating the future trajectory u of 1 to t, given the initial state u0, and then the gamma parameter. And then the previously introduced control task is generating the full state sequence, and then the full control sequence, and also optimizing some objective. And then the other 2 tasks can be also cast in this generation perspective. Then in this new work, we are unifying these 4 tasks into a single generation task, where through a single model, we can do any of these 4 tasks. And this work is done in collaboration with Disha Fan. So our model is called FluidZero, which is like constructed in the following way. Basically, we are modeling the joint distribution of the state sequence, the control sequence, and some parameter gamma, such as the Reynolds number, and so on. And then we use a diffusion model that trying to model the joint distribution of all these different modalities. And during the training, we can train this single model across these 4 tasks. For example, if we want to train the model with the simulation task, we can fix the initial state and the parameter gamma, and then train the model to denoise from Gaussian to the trajectory of the state. For another example, suppose that we want to do the design task, we can also train the model to generate both the state trajectory and the gamma. Therefore, through these 4 tasks of training, we can let the model to generate the missing modalities given some other modalities that data are given. And then we also have some model-specific encoders to embed different modalities into tokens. And then we can use spatial and temporal attention to model the correlation and the mutual influence of these different modalities. So I will give some result of the task. Basically, our finding is that our single model trained across these 4 tasks outperforms the specific model that are trained on some specific tasks. So here is the flow through a single cylinder, where this is the ground truth, and this is our model's prediction. And the second row is the error. And then these are a few other baseline models. And we can see that our model achieves the lowest error compared with the ground truth. So here is the double cylinder, where we can see that the FNO has the highest error compared with the ground truth, and our model has the lowest error. And this is the flow through a single foil, and then flow through double foils. And we see our model performs quite well. And then also, after training in the simulation data, we can also fine-tune our model with the real-world measurement. Basically, we can collect some real-world experiment data and then fine-tune our model with the real-world experiment data, and then test also on the real-world experiment data. And we see that our model achieves the lowest error. For the second task of the parameter identification, we want to identify, for example, some parameters like the drag, the new, and then our model can achieve the lowest error. And then for the design task, we want to design the airfoil shape such that the lift to drag ratio is maximized. And our model outperforms the backpropagation baseline in terms of the lift to drag ratio. And we can also, after designing with our model, we can 3D print our model and then put it in the real experiment And in the real experiment, we also see that our models lift to drag ratio also outperforms the backpropagation method. Finally, we also have the control task where we want to control the like rotation speed of or the rotation angular velocity of the cylinder such that we want to minimize the drag or maximize the lift. And here the red part is the no control region and the yellow part is control region. We can see that after the control initiates, the drag quickly goes down and then the lift quickly goes up, which shows that our method can control the system in a good way. And here we also have several other like experiment where we, after the control starts, we can minimize the drag and then maximize the lift. Finally, we can, for example, like see our model whether we can generalize to even to the parameters that are not seen during training. For example, after we have designed our airfoil, which in the training time has only seen the Reynolds number from 1,000 to 10,000, we put it to, for example, Reynolds number up to 100,000. And across this very high range of new Reynolds number, our model's lift to drag ratio still outperforms the baseline diffusion model, which shows that our model has a very good generalization across the parameter range. Okay, so here it concludes my talk, my talk today. So in summary, in the WDNL work, we introduced the generation of the diffusion model in the wavelet domain such that it can model some spatially abrupt changes and also perform simple resolution training. And then for the FluidZero, we unify the simulation control, parameter identification, and design into a single generative model so that it can use a single model to do either of the 4 tasks and achieve a better generalization. And here is my group. So my group has a very interdisciplinary background from physics, CS, automation, and so on. And welcome collaborations. Yeah, thank you very much.
Thank you
And
so
if you have
much.
any questions, yeah, welcome to ask.
Yeah,
Hi,
thank you.
hi, Tailin. My name is
Mhm.
Vivek. I'm a PhD student working with Professor Karniadakis. Great
Mhm.
work, very cool work. So I have a few questions actually. So,
Sure.
so the diffusion model that you're using what is the neural net architecture you're using? Is it a unit based?
So in the base model, the epsilon theta, I use the UNet.
Right. So my question is when you showed if I understood correctly, for a 2D plus time system, you do the wavelet transform, obtain the coefficients, and train the diffusion model to learn these wavelet coefficients in the 2D plus
Yes.
time wavelet
Yes.
domain. So if you
Yes.
have like 3D plus time, would you don't have like 4D convolution. So it's a very technical questions, but just want to ask.
Sure. Yes. So in the 2D, I will have two spatial dimension and one temporal dimension. Therefore, it is like 3D. So
Yes.
if the spatial is 3D,
Yeah.
it will have 4D. Yeah, it will be much harder.
Right, right.
Yeah.
So like the default platforms like Torch doesn't offer like 4D convolutions to my understanding. So that would be a challenge.
Yeah. Yeah. At that case, maybe we shall use the 4D convolution.
Right, right. Okay, thank you. And I have one more question, which is so I understand like you have a system at a certain resolution. You take the
Mhm.
wave transform at some subsample resolution, which ensures like the Nyquist frequency of that grid is greater than the characteristic frequency of the system. Now, my question is, how is the performance in terms of computational cost compared to training the diffusion model directly in the physical space at the least possible physical resolution versus the wavelet domain? Did you understand my question, or was it a bit too long? I can repeat.
Yeah, you're asking like compare with the like diffusion model in the original domain.
Right. For example, let us
Yeah.
consider this system, this slide you're considering here. So let us say you can represent this system without any loss of information using a 64 by 64 grid.
Sure.
So what is the computational cost against training the diffusion model on the physical 64 by 64 grid against the wavelet domain corresponding to the 64 by 64 grid?
Okay.
Is it
So yeah, here I also bring the first author of the paper, Pei Hu. Maybe she can answer this question better. Like for example, how much training time compared to the original space? Yeah, Pei, can you answer it?
Actually, when we are doing the experiments, we find that first, after the wavelet transformation, we find that the wavelet coefficient that we got has almost the same size as the state in the original space. So as for the memory cost, it's almost the same. And because we have done some transformation also on the data format, because we concat the wavelet coefficient. So there are some something like the readout time cost. It is not the same between the wavelet coefficient and the original data, because their data format is not the same. And after our transformation on the data, we found that actually when we are using the wavelet coefficient, because we have already concat these data, so we find that the training time of the WDNO is also smaller than the training cost in the original space. Yeah.
Sure. Thank you. That's all. Great talk and great work with Payan and Tailin. Thank you for answering my questions.
Yeah, thank you.
Thank you so much. Do we have any other questions for the speaker? Yes, Jensen.
Yeah. Tailin. Hi, Tailin. It's a nice talk. I'm Jinja, a postdoc here. I have a question about the second part. So where you unified four different cases in a framework. But I think especially for the design case and the parameter identification case, actually it's a PDE constraint. For example, the design is a PDE constraint optimization problem. So here actually the physics plays a very important role, and the connection between your design variables and the performance is somehow highly nonlinear, governed by the PDE. So my question is, do you use any information from the physics, or just rely on the data itself?
Yeah, very good question. So in this work, we only use the data to learn the distribution. And for example, we give it some different shapes of the like airfoil or the cylinder and so on, and then together with the flow through it. And then in this work, we do not add any physical like information, but if we want, we can also add it through the JD here, where the JD can include the design objective, like minimize the drag, or it can include the pin loss. Yeah.
Yeah, I see. So in that case, if you have a parameter space, several dimensions, you have to fill that space somehow, use data and use that as a training data set to perform a design problem within that parameter space, right? So you need somehow more data to fill that parameter space.
Do you mean that I need to like reconsider the different shape of the design and the
Yeah, I mean,
other?
so if you like a shape optimization or shape design problem, you have some shape parameters, and this kind of
Yes.
parameters will span space, and you have some limited range. And in that case, you need basically you need to fill that space use data. Otherwise, you cannot, I mean, predict the performance with that space, right? So
Sure,
means
yes.
the data, I mean, is maybe the generation of data is a large task.
Yes. Basically, in the training time, we also need to generate maybe different shapes of the this solid, and then it also needs to have some variations, diversities, so that it can in the inference time you can generate it well.
Okay, yeah, thank you. I like this unified framework. Nice talk, thank you.
Yeah, thank you.
Do we have any other questions, Alan?
Yeah. Hi, Tailin. My name is Alan. I'm a PhD student at Brown. I had a question about the 2D smoke control problem.
Okay.
So there you're trying to control this, you're trying to apply forcing outside your domain such that the smoke passes through the bucket, right? So here
Yes.
the control objective J is used only during inference, right? Not during training, you don't use the control objective J, right?
Correct. The J is only done in the inference time, where we integrate the smoke through this exit. Yes.
Okay. So could you tell like how the data was generated? Like, so are these forcings applied randomly, or do you use some simple controller such that the smoke gets close to the bucket and data?
Actually, let me see. So actually, there are two ways to do this J, to do this J. So one is that in the training time, we do not consider this J, and only in the inference time, we add this J as a guidance. This is one way. The other way is do the conditioning, where in the training time, we have two modalities. Actually three. One is the like control sequence. The other is the trajectory of the state. The third is the J value. We model these three joint probability of these three modalities. And then in the inference time, we can use the J as condition. So Peiyan, which one do you use?
Actually, we use the guidance one.
The first one. So in the inference time, only in the inference time, it has the J.
Okay. So when the training data was generated, are these forces applied randomly, completely randomly, or do you like somehow control the forcing such that the smoke gets close to the bucket?
We have some, the force is kind of randomly, but in the training case, it may not go to this. It may go to this or the left or right.
Okay.
It has different samples.
Okay. All right. Thank you.
Thank you.
Do we have any other questions? Yes. Can you introduce yourself?
Sure. I'm Professor Wen Smith from Yale. I have some question about the experiment results, especially the first table. Can you go back to the first table?
Okay.
Oh yeah. So first, each of the model is trained to predict from t to t+1 and do the auto regression prediction, right?
So here, it is we use our model to predict multiple steps into the future, not only one step.
Okay, and also the data used to train or the initial state of the data is do not have any noise, right?
Right.
Okay, and a final question is for the DDPM methods, is the sampling method also DDPM or a more deterministic method like DDIM?
Here it is DDPM. We use the full, like maybe 1,000 steps of denoising.
Okay. Yeah, I'm just quite surprising that in one DPD problems, DDPM would outperform other methods like FNO and the UNet because in my experience, DDPM often do not outperform a more deterministic method like your operator. So yeah, so I have these doubts.
Yeah, actually here the FNO also performs quite well. Yeah, this is a quite easy task. Yeah.
Okay. Then do you use ensemble methods like for ensemble like from 10 results for the DDPM forecasting?
No.
No.
I just use each of the sample. One sample just as the prediction.
Okay. Yeah, thank you very much. Great talk.
Thank you.
Do we have any other questions, comment?
Hi, this is Farsha from NIT. I love learning about the whole model architecture. My question is about the WDNO experiments. You use the Bayer 1.3 and the Bayer 2.4 wavelet classes. From your experience, how sensitive is the WDNO's performance to the chosen wavelet family when applied to highly anisotropic or graph-based, especially PDE datasets?
Okay, so this question may be answered by Pei Yan. You maybe have done some test.
Yes. Actually, when I conducting the experiments, I found that the kind of wavelet family is actually very matters a lot, and we find that especially the wavelet families have many levels of different basis functions, like there are BIOR like one and also BIOR 2 and the functions like that, and the number denotes the length of the interval of the basis functions, and we found that the length of the intervals should actually match the state of the system. Like if your system is only taking values in very small regions, then you maybe need to also use the basis functions with shorter length of the intervals. And if your if the features of your states is quite large, and then maybe you need to use the longer intervals, yeah, something like that. So I think in sum, the kind of wavelet family you use is will influence your model's experiments. Your model's performance a lot. Yeah.
Thank you so much, and thank you again for the talk.
Thank you.
Thank you. Do we have any other questions? I don't think so. Thank you so much for your great talk. And I think it's like, thank you for staying up late for this presentation. Yeah, it's time to close the session. Thank you everybody for joining us today. Have a great weekend. Bye.
Bye-bye.
Bye-bye.